Okay, how many of you have seen a movie called Men in Black? Just put your hand up. Oh, 1, 2, and L, of course, you've seen it. Well, I better tell you what the movie has in it. It reminds me, for as far as physics goes, interplanetary physics and astronomy, Enrico Fermi, one of our greatest physicists, asked a question as he looked out at astrophysics and the sky, and he says, "Why is it so quiet out there?" And he's talking about why we haven't heard something from an advanced civilization. And this is the beginning of SETI, which was the search for extraterrestrial intelligence. Well, The Men in Black is a sort of a comical movie that says it isn't quiet out there. In fact, we have a vast underground place for all of the interplanetary people to come, sort of an airport for the universe, and there are all these crazy creatures running around down there. And the Men in Black were the people that took care of making sure that these people behaved well. So that was the premise of this movie. But in order to get in, you had to take a test, and the test was just like a test that you'd have for a police, where you would have all sorts of dangers and things brought before you, and you would have to learn not to shoot the good people, but you had to shoot the bad. And in that test, one of the candidates, and if you remember the name of the actor,
Will Smith.
Will shot Susie. And the question is, why did he shoot little Susie? Now, this is right out of the movie, and you'll notice, if I blow it up here, that there are 2 books, Quantum Physics and Relativity, and that's what we're going to talk about today. But the point I want to make is that Susie was shot. She's bad. Relativity and quantum theory need to be in a single book. Half the size of the big tomes that you carry around. That's what I'm going to try to show today. And we call this relativity. So we start by thinking of electromagnetic waves and take from them the geometry they give us. That's what's going to be the 2 chapters of the lecture and the little piece of Unit 8 that is a substitute Unit 8 that I have given you. So, the basic idea is that all of the wave mechanics is just based on really simple stuff, as you see here. And since we're in Arkansas and we just had an election that involved somebody that was quite sinful, saying this is learning about sin. Okay? And there's the button right there. So pushing those buttons and others like them, there's also cosine. But anyway, sin stands for slope of incline for us. And the sine and other functions are what we're going to first take a real quick look at, the geometry that goes with them. You've all seen this, and you've seen the cosine, complementary slope, and that all can be put in sort of a nice diagram, and we'd like to improve on this diagram right here, that has all 6 of the functions that you can get by taking these 3 and then their inverse functions and pushing buttons to get the numbers. But what I would like you to think just a little bit differently about these functions. And here we're showing it as an angle, which it is, and I'm picking a very special angle, 36.87 degrees, that gives you a nice 3, 4, 5 triangle. Every one of the triangles that make up the structure that defines the 6 functions, sine, tan, secant, and cosine, cotangent, and cosecant, are in appropriate positions. A tangent is on the tangent, and there's the complementary tangent. A secant means sort of piercing something. The piercing all the way to the center is that, and its complement is on the other axis. And then, of course, sine and cosine are in their places. It is a little different than what you're probably used to. You most likely like to have the cosine down here and the sine over here. There are reasons why to make our relativistic trigonometry that we do at this particular setting. So the idea is that all this physics of relativity is mostly simple trigonometry. And the trigonometry that optical wave interference gives us. But what's really neat about it is if you approach relativity that way, you also derive the fundamentals of the quantum, relativistic quantum, actually. Now, we have animations here that allow you to play with this thing. I'm going to kind of skip very often here. We'll pick up on this in a few minutes, but the main thing that I want, as you can see, it's getting complicated now, because what I'd like to show you and use, and this is more common for relativity, are the hyperbolic functions. Each one of the hyperbolic functions, tan hyperbolic, sine hyperbolic, cosine hyperbolic, secant hyperbolic, cosecant, and cotangent, has a partner that is equal to it, where we have as the row here also an area. Now, the thing that I was about to say about this is that rather than talking about the angle, we actually are talking about a sector area. This whole thing here that's in red, plus what is below there, that area, okay, is what we're using as the independent variable of the trigonometric, ordinary trigonometric functions. The hyperbolic trigonometric functions are sectors of a hyperbola. So instead of x squared plus y squared equal b, our base squared, this one is y squared minus x squared is equal to b squared, an equilateral hyperbola with asymptotes at 45 degrees. And that's the one we'll use first for doing a development of relativity and eventually quantum. But the thing is that this other set of functions can also be used, and that's not realized very well at all. It really needs to be. So when we talk about a hyperbola and its sector, this green sector here, which goes all the way up to hyperbola, and then there's another branch of the hyperbola down here that holds one just like this. That area is the row. Okay. Now there's an angle associated with it. We call it nu, for lack of a better name right now. That angle, actual angle of that, you see, is just a little bit less, 30.96, than the angle that goes with the sigma, this 36.87 thing. And the area is quite a bit more. This right here, 6931 compared to 6435 for the red area. But given those two numbers, the rho is the area of the hyperbolic sectors, and the sigma is the area of the circular sectors. Then you have the sine, ordinary sine, equal to the hyperbolic tangent of the rho. And the ordinary tangent is reciprocally equal to the hyperbolic sine. And then the secant and the cosine play same game. The secant is equal to hyperbolic cos, and the cos is equal to the hyperbolic secant. And then finally the inverse functions do a similar dance. So this is what we're, this is, just basically something that should be in every middle school and high school education. This makes the trigonometric functions less of a bore and more interesting. And you get two for the price of one. And in fact, the hyperbolic functions are the ones you should start with. So no imaginary numbers involved there, at least not on the surface. Okay, so putting all this together, we make a diagram. Looks pretty complicated, but if you put it in there by step, which we will try to do today, you will see how it goes. And I should probably quickly show you that just by, and also check out our animation system and see how it's going here. It takes a little bit for it to pull it up, but this is that diagram. Turn it on the side, okay, and there's a reason for doing that. But all of these functions, you can see them doing their thing here, and you can go all the way around and fill the thing so that you have pi. That's what you would call 180 degrees with the ordinary sigma, but the hyperbole, you see, just takes off and goes to infinity while this is going. So this is really a beautiful geometry that we're going to see from simple wave interference. That's what's coming now. But as it stands, this is a neat thing, just the mathematics of trigonometry. Plain two-dimensional trigonometry. Okay, so let's get back here and go ahead a little bit. This is a diagram that I'd like to arrive at by the end of this class. It's the same diagram, but all of the quantities that you learned about in this class, like the Hamiltonian, the Lagrangian, velocity, momentum, and then some other things we didn't learn so much about, de Broglie wavelength and phase velocity, as opposed to group velocity, they're in here too. And so this is the diagram that the physicist, I would hope, after some years go by, likes. Now we're hoping we're going to be able to get this thing into the Springer Handbook for Atomic, Molecular, and Optical Physics. Gordon, who's the editor, has said, well, let me take a look. It sounds interesting, and we'll see how that goes. But anyway, as I said before, when it comes time to actually do the algebra of all of this, and I mean high school algebra, it really helps to start, as we did in this class, in chapter 10 of the first unit, make it based on money, okay, the root of all evil, okay, the interest rates, the banking part of the economy, in which if you compound many times in a period, n goes to infinity, you get an exponential. And we looked at that in some detail. This binomial expansion carried to the limit, n infinity, is the expansion for the exponential, or the minus exponential, in which all of the odd terms have minus signs. So this is much easier to derive first if you're just going to teach trigonometry. Hyperbolic trigonometry is more fundamental than circular trigonometry, which we're going to get by simply putting an imaginary interest rate in there, as you saw in our development of both the simple exponential and also the exponential exponent in Unit 4. In any case, replacing r with that gives you this, and then you have basically the same kind of relations. That's this, and plus this cos plus the sine, cos minus the sine, and then half differences and half sum and half difference. This is important right here. This half sum and half difference, in particular, sometimes this one, but this is the one we're going to be dealing with. We're going to be dealing with the function rho for our hyperbolic cosines. And so there's the sum and difference giving the exponentials, which is just the equivalent to the Euler-de Moivre relations between trig functions and exponentials. Okay, and that's kind of all the algebra we need for this. This is it. It's high school stuff. Okay, that's what I'm trying to get across here. Now we use the imaginary, the cosine sine exponentials as phasors, the clocks that define space and time in some kind of field that holds, some kind of area that's holding a field. Basically, it could be in a one-dimensional cavity. And that's kind of what I'm imagining here. But if it's just a plain old 300 terahertz laser beam, an infrared laser beam, and you could look at it very closely at its wavelength, which is a micron, okay? We have a 1 micron wavelength here, lambda, and we're going to go over all of these quantities in just a minute or two here. And then it has a certain period, okay? We're talking about basically thirds of femtoseconds, 10 thirds of a femtosecond is the period for an infrared beam that's operating at 300 terahertz. That's what this laser is. But the thing that I want you to start thinking about is all of these phasors, every point in space and time, and if there were more dimensions in space, 2 more is all we need to finish this, they all have something that is keeping track of time. And right here, you see, I put the lines of constant phase there. So as this thing moves, that's what it lays down. If this wave here is going to move, there's its imaginary part, there's its real part right there. That's what we're going to be dealing with. That's where this trigonometry becomes important. And there are 2 extremes to this that are mentioned, and I might as well do it in this slide right here. But before we do that, take a look, and we can swing the camera around to the extreme screen down on the right-hand side there, and you'll see, going left to right, a dark cosine curve. The dark regions are the troughs, the light green regions are where the crest is at any instant. That the dimension of the vertical axis is 5/3 femtosecond. That's the period that we're talking about here. And the cross is a micron. It's essentially this plot. And you'll see the phasors down at the bottom there, all showing what they're doing at a particular instant. But the idea is to think of a phasor sits at every point in space and time. That's the world record of the phase in this little model that we have here. And so the limit is what we're doing here, and that is we've got a bunch of clocks that are standing still right here and turning at the rate of 300 rotations per trillion rotations per second, 300 terahertz. But the other way to do it was to just have clocks that don't turn at all or very little, frequency 0, and make sure they're all going at the speed of light. All of the stuff we're going to talk about are between these 2 extremes. That's called gauge invariance, as though a gauge was a clock. This is Weil's terminology, and I don't think he had as clear a physical concept of what this is. But the basic idea of gauge invariance is that no matter how fast you're going, that clock field is reading correctly for you. There's one clock field, no more. That's all you need. Now, that's weird. Now we've got to do some geometry before that becomes clear. But that is what we're dealing with here. Something really quite remarkable. We're also dealing with the concept of space and time, but the thing that makes this relativity powerful is to instead look at Perspacetime. That is the inverse of space and time. So I want to go through this diagram piece by piece to really make it clear. But everything in blue here is going to be inverse seconds, frequency per seconds, okay, waves per second, versus waves per meter. How many waves do you have per meter? That's called a wave number. We've got to get used to that variable. So getting used to this space here, which is Heinrich Kaiser's space, and we'll talk about him in just a minute. But you've all heard of Heinrich Hertz. He takes care of this axis. Kaiser takes care of this axis. Okay? We feel we understand what space and time is. Do you? Well, I don't know. There's some more to learn about that. okay? But the basic idea is that wavelength, that's meters per wave, just the reciprocal of waves per meter, and here, up here, waves per second, okay? Seconds per wave, okay? That's what we're talking about. This is waves per second, this is seconds per wave, this axis, okay? That's just space and time, but it's wave space and time. Okay, so let's start off here. What's the deal? The way I like to think about this, first of all, is it's Fourier analysis. This is the Fourier space, or some people call it dispersion space, and we'll get the reason for that name shortly. But the idea is that you think of this as the keyboard of the gods, that's what I sometimes call it, in the sense that you can get any frequency you want, just like you can on a good keyboard, within a range, of course, nowhere near the frequencies we're really talking about. Can't hear them anyway, you got to see them. But anyway, the idea is you can press the key anywhere on this axis or here, get any frequency you want here, but here you're actually naming the wave number in space. How do you, without being a god, how do you do that? Okay, so this is a super musical instrument in some sense. All right, so this all have the same frequency, but they have different wave number. And all things along here have the same wave number, but different frequencies. And we got to get used to thinking about that. But the idea is that each point in here is a key, a button, to make a wave. It makes a wave. And it doesn't just make that thing. It makes a lot more of those things. Fills the space and time with them. Just this one button here fills the space and time with those things. Okay, that's a concept that's, I think, really understandable. I think it makes sense out of Fourier analysis. You get waves in space and you get them in time. You get something at a certain wavelength and a certain period. Okay? And this is period axis, seconds per wave. And the other one is Kaiser's, what Kaiser has inverted right here. So, Greek time, tau, perfectly good letter that everyone uses. And that is 1 over the nu value, the frequency value, nu. Now it isn't really nu, that's omicron. Nu looks too much like V, so I don't use it. I use this thing. Okay, instead. Okay, so the idea is you push this button and you get both of these things, but you get to fill the whole space with those things, whole space-time with those things. Greek L, lambda, length, okay? 1 over this kappa here, okay? Remember, everything over here is inverted over here. So, basic idea then. Okay, so Kaiser is apparently the reason for the K of the wave vector, which you learn about right away anytime you do some wave mechanics, right? Apparently it's this guy. Now look how closely their birth dates are. Okay, 53 and 57, only 4 years apart. But this guy is an amazing solar astronomer, and the Kaiser is 1 inverse centimeter, and if you're doing chemical physics, you'll see that all the time. It's an infrared wave unit. Waves per centimeter. Okay? So that's what it's working, so it gets named after it. I say it stands for kinks in the wave, okay, is one way to think of the K. But look at, he is much more healthy. He dies in 1940. He dies in 1894. Quite a difference. What does this tell us? We really need to know about this axis. It's a healthy axis. Okay, we know about this one. All right? Okay, so that's the basic idea. This is the Fourier space. So let's start just with a basic idea and say when I push this button, sure enough, I get that one little wavelet there, but what that means is 1 CW, one single continuous wave is the notation I'm using here for pushing one button right here. Now you can have, how wide is your button and all of that. That's what Fourier analysis is about. But I'm just imagining that this is as big as one of those pixels, for example. And when I do that, you've got to realize that this continuous wave continues everywhere and for all time. You literally fill the whole universe with this wave if this is a perfect button here. Really the keyboards of the gods. Okay? So this is the extreme case of a pure wave. Pure, we mean electromagnetic wave. That's what we're really dealing with here. Now, just for the heck of it, let's go ahead and see if I can get this guy to work a little bit, just to give you an idea what happens when you click on this thing. And there we go. Okay? So the basic idea is here, I grab this button and I put it anywhere. Okay? Now when I make this thing one big, the waves get small. If that's the reciprocal, right? When I go up in temperature, I make it small in the t direction. When I go down here, I make the periods longer. I come in here with a small wave vector, I'm going to get a big long wave by doing that. Okay? So this is, you know, kind of a neat thing to play with if you're going to be using this to teach students about waves. Okay? All right, enough said for the moment on that. Now, with that comes velocity. Once I've seen how much the wavelength is and how much the period is, and I want to know the velocity, well, distance over time is velocity. So it's wavelength over period. That's the quickest way you can say that this formula, lambda over tau, is going to be giving me a velocity. Now I've got 2/3 over 5/4. I'm using fractions throughout this lecture for all of the quantities that are in the 3, 4, 5 triangle that we'll use to display relativistic situations, most of the cases. Okay? So with this period and with this wavelength, I know that I'm going to be getting a velocity of that ratio, 2/3 over 5/4, or 8/15 meters per second, if we're talking about MKS units here. Okay? But we can also look at a ratio up here. You see, we can look at the ratio here of kappas to nus. Okay, so that's the idea. Lambda over tau, then the reciprocal of lambda is kappa, the reciprocal of tau is nu. That's just another way to write it. Okay? Both of them better come out to the speed that we just said. They're 8/15 meters per second. Okay, so that's the arithmetic. Pretty good. It looks easy. That's what we're... Now, just one slide here about Doppler shift. We really need more, but we're kind of rushing things today a little bit. So here we are with a situation where we have Perspacetime, and I've got a particular button pushed, the green button, and I get this wave right here. And then I go over here in the space-time, and instead of standing still, I maybe start running along this path. That's a positive velocity of the observer. And I can see that what I'm doing is I'm running sort of with the waves. If these were water waves and I was in a boat, I might get up, you know, in a boat I could get easily up to the speed of the waves and just, you know, follow in the trough of the wave. That's the way a good seaman comes into San Francisco Harbor, where you're talking about waves of the size of this building. He tries to get in the trough and just ride it into the harbor. Going back out again is another story, because then you're going to be hitting a lot more often. Now we're talking about light here, so when we're talking about light, as you already know, frequency means energy. We're going to prove that, but that's something that's ingrained in our education. Okay? But anyway, the idea is if you move fast enough this way, then this green wave gets redder and redder. That means more and more infrared. It also shrinks in amplitude until finally it dies. You just don't see it anymore. It's gone. You can run away from a light wave as you approach the speed of light. Okay, you just bring it down so the amplitude frequency is nothing, right? It ceases to exist essentially for you. Okay, or you can go the other way and try to get that speed of c going. Okay, not I'd recommend it because it's getting bluer and bluer. I mean gamma bluer, and you die. You go really fast into a green light, it's going to be some super gamma radiation. You're dead. Light's not dead. Okay, so these are the two extremes of Doppler shifting. Okay? And remember, we're also going to be using angular units, so we'll be seeing this ratio for the letter C. But what we have to talk about is something that really is a showstopper for every relativistic book or course that you've ever seen. This is a showstopper. Why is C constant? Oh, in particular, why is it so constant? And if you're Fermi, why is it so slow? You go out at night, and there are all these things that are hydrogen bombs that are going off, okay? Hydrogen bombs of hydrogen bombs, right? And when you, if you were the first to look at the sky when you were 5 years old, take a picture of it, very accurate picture of it, and look at it just as you're about to die, it's pretty much the same. It's only with really powerful telescopes that we see these monsters out there actually move. Nothing goes faster than light. Well, when I say nothing, something as quotes have to put around that, because we're going to find out half of everything goes faster than light. But in the meantime, the kind of stuff that we get to work with and touch and visualize is limited by this. And the question is why? How can you see that as a logical thing, not just something that the great Einstein said that you have to bow down to as though it were some kind of religion? Okay, so that's what I want to try to make things. So I'm going to make up this situation for the rest of the lecture, in which we have the usual thing that quantum opticians like to do, and that involves some sort of play acting between Alice and Bob. Basically, you're talking about light going from A to B, so we put some names on them. So here's Alice with her laser. She's shining her 300 terahertz laser, and I've got it slanted because, unbeknownst to Bob, she is moving really fast. Okay, but she talks to him and says, "Hey, what do you got for frequency?" And he comes back with this. My frequency meter reads 600 terahertz. That's what we're going to do. We're going to look at situations where laser light is being viewed by something that's moving, or by you moving, that doubles the frequency, an octave shift in frequency. But in any case, we're imagining a situation where Bob doesn't even know that she's supposed to be staying at home, but no, she decided to get her rocket ship going, and as she goes forward, she originally had a 600 terahertz laser going, and he was asked to say what the frequency was, and it was 600. She is very cleverly down-tuning the laser as she accelerates, and she stops accelerating at a certain speed, which we'll calculate, that makes him still see 600 terahertz while she is sending infrared at 300. So the question is, okay, that's the frequency you're reading, what's your wavelength? That's a entirely different measurement of light. You're now going to fit it in a box or something instead of in a time period. Orthogonal measurement of this thing, okay? But in any case, you can ask the question, Alice is 300 terahertz opposed to Bob, Bob sees 600, what lambda does Bob measure? And a better question is, how many different beams are there that have 600 terahertz? Maybe there's one here, B. One here, A. Here, C. See, you've got that one a little thicky, so that's probably the answer. But here, maybe D. Could be, it could be something that was much higher in its wave number. Okay? So, and the question is this just a phony green, right? This was made by a 300 terahertz laser. That's really the question, okay? Well, you can argue this all day, but years of spectroscopy rule out a phony 600 terahertz. Half a micron is what you get for 600 terahertz. That's 4-figure accuracy. Okay? So, only choice here is C, the same thing that Alice had when she started with the 600 terahertz. The vacuum is made by the lowest bidder, and it just doesn't have any other modes at 600 terahertz. That means it doesn't have any other speeds here or here at 600 terahertz. That's the real catch. That's where it becomes logical that it has to be, this slope here, C, is a constant. So this ratio of frequency to K, kappa, or omega to K, that's got to be what it is. 3 times 10 to the 8. Well, really it has to be, and this is Ken Evenson's measurement, it has no plus or minuses, it nails the definition of the meter, which is not measured as accurately as he was measuring time. And that's still true, as we've increased our precision of measurement time to the 19th exponent. We still keep this number, and we will for probably some time. Okay? So that's getting rid of this idea that, you know, you're going to be able to exceed C, and all that. That's got some problems with it. But the basic idea of seeing any light at any other speed is verbal here. Okay, and the other thing that's important is that means that all of the colors march in lockstep. And I call that Evenson's axiom. All colors go the same speed. Okay? That's called dispersion free. That means if you make a Fourier combination of some piece of light that looks like that, it's got to march along without changing. It does not disperse. Okay? And we see this in astronomy. We see light that's been around a gravity lens, right, coming to us without dispersion. If even 0.00% difference between red and green in velocity, so that a particular green signal showed up, say, earlier or later, by that percentage, that means millions of years late, if you're talking about the galaxies we look at, billions of light years away, the sky would just be full of psychedelic rainbows. So there's another way to get through the roadblock of the C constant, which has got to be broken down before we begin revising our way to do relativity. Okay, now there's one other thing that we want to introduce here, and that is how you measure frequency really conveniently. And you have to realize that Mr. Galileo had his idea of the Galilean addition of velocities, which we made a big fuss about on the first day, right? He had that broken. We all know it doesn't work at high speeds. The velocity parameter doesn't add correctly to give you the velocity that you see to be due to your motion. But there is a parameter that does that, and that's what we call Galileos Revenge Part 1. And that's what I want to show real quickly here. Normally we'd spend more time on this too, but this is the idea where not only I'm going to have Alice and Bob, I need Carla, and we're going to need her for some other things to do, because they both got lasers that are going to shine on Bob. But the basic idea is, if you define a quantity, receiver over source, and you write it with direct notation, and what you really are kind of thinking of is R slash S, R over S, okay, instead of the quantum mechanical thing, and you take the logarithm of that, you get that parameter that we've been talking about that goes with the hyperbolic functions, rho. I'm using rho, it's kind of a flipped over sigma, and we've got sigma's got an astronomical definition as well, which we'll bring up later. But this is introducing arithmetic and the of this quantity rapidity. Okay, so Bob and Alice have some ratio of frequencies. Well, we can just read it off here: 600 over 300. 300 is the source. Okay, so we're talking about a quantity of 2 to 1. Right? That's Bob-Alice rapidity. Logarithm 0.69. Okay. Now, if Bob was the source, or you just turn this whole thing around, okay, you get a minus rapidity. Okay, Alice relative to Bob. He was the source. So they're doing a time reversal to get that. Meanwhile, Carla and Alice also have ratios. In this case, 4/3. Now, Alice is going here at a higher speed than Carla, way higher than Bob. He's standing still according to us. She's actually running away from Alice. Okay. But anyway, the Carla-Alice rapidity also positive, and that's a little annoying when things when things are let's see if we've got this right here. This is Carla relative to Alice. This is the logarithm of 4/3. That's a positive number in the sense that they're approaching. Okay? Here they're really approaching. How do you remember this? I think I would use a romantic mnemonic. I would say, let's say they're all friends, okay? When you're approaching, it's positive. Okay? Oh, good, you're coming. Departing, oh, well, we'll see you later. Okay, that's negative. Okay? That's just the opposite of the way you treat polar coordinates, right? This is positive, right? Moving out. This is negative, coming back. This is just the opposite. Okay? Of that, as far as the sign goes. All right? Now, when we use those things, and this is where Galileo gets his revenge, if I want to figure out, as is in this cartoon thing here, what's the relation between Bob and Carla, given that I know what's the ratio for Bob and Alice and Carla and Alice, okay? So this is Carla relative to Alice, this is Alice relative to Bob, okay? That should give me Carla relative to Bob. But I have to know A over B. I have to know this one, okay? So you multiply those two together and you get 2/3. And that is Carla relative to Bob that we're going to be seeing here. So Carla-Bob rapidity, you use the exponents, just like the reverse of the definition here, okay? And this time, because you're using this negative thing, you get this value here. They are separating, and you can see they are separating, and that's exactly the rapidity with which they are separating. So you can draw little rapidity diagrams that are just like the diagrams for velocity addition. Okay, that recommends rapidity really highly. And of course, you can see this is one of the few pictures of Galileo where he's smiling. He's very happy to have gotten some revenge for losing out on velocity. Okay. Now we got a second one too. And this is real fast here, and I wish we could stop and do this, but right now the Pirelli system has gone into the future, so to speak, and been left behind, so you won't get the animations of these phasors. But this is what we're going to be seeing. We're going to be seeing half sums and half differences between various kinds of frequencies, velocities, and other things. And the idea here is that when you talk about angular velocity, you also add using Galilean addition. There's no fancy business, even at very high frequencies, that there is for very high velocities. So he wins on two things. The rho replaces velocity, he gets to have his way of addition. All right, now, here's where we really should start this discussion. And this kind of will be the start of the discussion if this thing goes into the handbook of the DAMOP handbook, the Division of Atomic, Molecular, and Optical Physics. And that will be, how do you make a space-time coordinate system using plain old laser waves? 1 CW, continuous wave lasers. 2 of them. One of them, Alice is going to be here, Carl is going to be here pointing her laser backwards, and Bob's going to be in the middle. And this is very cool because, as you will see, and I will try to run the animation on this screen just to get its, see if it's working properly today.
Pirelli should be up, Professor
Pardon?
Harter. Pirelli should be up. I don't know what the issue was.
You want to go ahead and see
Yeah,
if it is?
if the link's broke, I can fix it by eye.
Yeah.
It'll be an old link.
Let's just go ahead and
Yeah.
see if...
You got to replace those PHPs with HTML, and you'll be in like Flynn. Those are
well,
old
that's nice
links.
to know. I wish I had remembered that.
We'll swap them out later.
I can do it right here.
Yes, sir.
I will take this.
And there's another one ahead of that too, so replace that one.
HTML.
You might as well undo your caps, but then do it for the other PHP that's right in the middle. Right
This guy.
there. Yeah.
Okay. You all got that?
We
this
have
is the
those
way.
swapped out somewhere.
Yeah. Okay. Now let's just see if she'll run. Okay, I'll just go ahead and return. I didn't get the button quite. Boom. There we go. There we go. Okay. So what we're talking about is interference. That's the addition of 2 phasors. Okay, these guys. A beat. When they're in phase, you see big amplitude. When they're opposite, you see nothing. Here's the Thales way to do that. Just get into the frame of the red phaser and watch the green go around your nose. 0 to max and back again. A little rectangle, Thales rectangle in there. Or you can get on the green one and the other one's going the other way relative to you, making that. That's the kind of geometry that's responsible for relativity and quantum mechanics. Right there. That's it. Thales geometry. Okay? Half sums and half differences being taken in a rectangle, or just with vector addition of the normal type. Okay. Let's go ahead and back out of that. Actually, what I have to do, I guess, is just go and start the thing again. Okay, well, that's nice to see. That's the Galilean addition of phase, right? And we've seen no sign of that breaking down like velocity broke down. Ordinary velocity, okay? So, what we're talking about here are the waves that you get when the 2 collide. Well, you know what happens when 2 waves of the same amplitude collide, and that's you make a perfect standing wave. But there's a lot to that standing wave, and that's what we need to talk about and understand. Now, while we're at it, the wave maker, the Bohr is the name of it. Just this morning, TC pointed several little fine point adjustments that we can make on this, okay? But for the now, I think we'll just let it run. But here's where we play. This is keyboard here. This is keyboard that has the kappa. That's the wave number, the number of waves per meter or centimeter. Okay, and here we have the number of waves per second. Trillions of them to be exact. But the units of this, I think I will normally take 600 terahertz as our defining unit, but sometimes we take half of that in the book that comes with this little lecture.
What?
In any case, this is what you get. Now, I guess it wouldn't hurt to get an animation going on that. And I'll do it over here. Just to where it should be clear enough what it is happening. So there you see the phasors at the bottom, like the screen on the extreme right-hand side. And then you see a standing wave in the middle. And that standing wave is making a coordinate system, a coordinate grid for space and time, with the units being half wave. In other words, you've got a whole micron across this distance here, and then a half micron is a whole wave, because we've got a wave with a number 2 as its frequency. And it's a light wave going this way or a light wave going this way. The two of them are interfering to make not a set of diamonds, but a square set, a chessboard, a checkers board. Okay? So that's the main idea of this way of approaching relativity and eventually quantum mechanics. You take these two spaces and map them out. Just using 2 buttons. You push 2 buttons and you get this. Now the thing to notice are the white parts. The white parts are the ones, and I'll point to them on here. The white parts are zeros for this sum of waves. And how do you get zeros for sum of anything? Factor it, right? We've done this once already when we're talking about beats. You factor that sum. So that's what's going to happen here. I've got these 2 waves, e to the I right hand, e to the I left hand. Okay? Left, right. Now right means right moving. Left means left moving. This guy's left moving, that's right. So this is Alice, that's Carla's. Carla's got left moving. She kind of looks left-winger, right? This is more traditional Republican, okay? She's going right, okay? And we're making in the middle here something that has zeros associated with the green envelope of this wave and zeros associated that really go fast. They go infinitely fast every once in a while, every half period. And that's the blue part. The blue part and its imaginary part are shown together there, being crunched by the envelope. Now, how do you make such a thing? Well, you factor it. E to the r plus L, r minus L, L's cancel. This is just e to the IR. And then I put a minus sign on that thing, and now it's the r's that cancel. And I end up with e to the I L by multiplying these 2 things. Then I've got a product where 2 important wave concepts emerge clearly. This is a real cosine. I color it in green, sort of, dark green, and it is the light green envelope being plotted there. So it's cosine k times, and there's a plane wave in there, but it's a plane wave that doesn't have any spatial dependency. It just has time. So it's just going up and down. That's what you mean by a standing wave. Now down here, there's where you talk intelligently about who's standing and who's moving. First of all, the G here, the group part, the thing that is the difference between R and L, okay, these guys, okay, the difference vector, and it's half of that actually, okay, half of R and minus L, R and minus L, okay, would be out here, but half of it is right here. And it's got slope 0, and it tells you what the group wave is going to do in space and time. And it's just going to go nowhere. It's just going to stand still as time goes on. Meanwhile, this guy right here, that's this guy, the phase part. That's R plus L over 2. You're going to add these 2 vectors right here. This is first base, this is third base. First base plus third base is second base. We want half of that, that's pitcher's mound. Right there. P for pitcher's mound, okay? Well, it's P for phase. This is the phase part of the thing. This is the heartbeat of this wave. This is the thing that's alive about the wave. The skin of the wave is, well, a skin is dried stuff, right? And tell me about it. If somebody like this, I've got a dust storm, okay? So, these two vectors flipped, because this is in inverse space, okay, define the lattice of an entire wave, of an incomplete lattice, the lattice that goes everywhere in space and time, for just these two buttons, these two perfect buttons. And that is, without some questions, as much as I'm going to say about this. We'll keep saying it again as we do something to this. But this is what sets us on the road to relativity, is being able to realize we should let light tell us what space and time, and inverse space and time, do. Once we get done listening to light, we start to understand things that we didn't understand very well before. Okay. Now I should point out the difference between a CW that makes a nice square set using just a baseball diamond and something that uses a whole bunch of Fourier components to make what we're doing now in getting really great metrology. This is what Ken Evenson's work turned into, and he, well, eventually died before this really happened. But let me go ahead and just really quickly show you what happens is you make a baseball diamond in space and time then. So if I set this thing up as pulse wave lasers, then those pulse waves crash into each other and continue without damage and make an extensive baseball diamond. They fill the whole space and time thing up with baseball diamonds. Okay? So that's the other extreme. One that's being explored more now than the first one. We've got our stabilized CWs. Now we've got to learn how to control PWs really well. And we are to the order of 10 to the 19th. Okay. Now, let me get this thing up here. I don't want to use up too much CPU time, so I'm going to pause a lot of our movies as we go along here.
The other one's laboring.
This one?
Yeah, it's got something on your CPU.
And that's on an older, slightly older power book, but pretty much the same system. Yeah, I don't know what's causing that.
Something's
Okay,
causing
let's put it to rest as well, because we got some work to do here. I'm going to pause her. Whoops, was that a pause? That's a raise.
2 buttons up.
It's hard to see.
Yeah.
There you go.
It's like
Okay.
working in a mirror.
So let's take both of these back home here, and go ahead, and this is what I want to do. This is where we take the baseball diamond and warp it. What we're going to do now is imagine a rapidly moving Bob. Okay. He, as you remember, when he approaches Alice, or she approaches him, there's a blue Doppler shift. Blue, even purple, okay, even violet, okay. In fact, ultraviolet, 1200 terahertz is what we're going to have coming in from this direction for Bob. And we're going to use the same factor in the denominator to describe what Carla's wave looks like. Also 600 terahertz for her, but it's going to be redshifted by the same factor, and that's due to the geometry of the waves and the constancy of light. That's a very simple piece of wave geometry that we're going to kind of skip over and maybe come back to later. But the idea that these things would add up to give you a coordinate system in space and time that somebody moving really fast would see. And we'll see exactly how fast by looking at that coordinate system. And we will also get the entire theory of special relativity in one fell swoop. So let's take a look at that, and I will do it on the weak machine here first, and then we'll bring it up on the better one. Now, if you want to simulate a wave moving on either side, that's just what you see at the end of the room there. I won't bother to do that, but I will go ahead and run this one. I think that will work okay. So let's give it a try. There it is. Now remember what happened, and I guess I skipped over this concept, was that when I had a sum vector here, and I'm going to go ahead and put the whole thing in here, what I want is a half sum of first base and third base, but now it's a warped, it's a marathon on first base, it's a short steal from first base to second base, a long marathon back to third, and then a short steal home. Half as much as you had to have, this is twice as much. But now we're going to sum this plus this over 2. Well, that's nothing but the center of a rectangle made of those vectors. There's the new P prime. Pitcher's mound used to be down here. It's now up here. And then G, I thank Woody for giving me a mnemonic for that. He used to call it dugout if we're going to use baseball. This is grandstand. Sit in the grandstand and watch the game off to the side. And that's kind of the perspective of the baseball field you'd see if you were kind of low in the grandstand. And anyway, that G vector and that P prime vector flipped make these rhombuses. These rhombuses that contain, as you can see on this diagram, which of course I can pause anywhere, and I'll pause near the top. Oop, that didn't pause, did it? Okay, try again. Pause. Okay, and you can see what's happening is the phase part of the wave, the zeros of the phase part of the wave are being traced by the cosine, by this, you see. There's a zero, that zero has been going in a straight line. Quite amazing. Okay? And then there's another free phase zero right there. That's the next one. And there's even one here where it's just passing through the group zero. The group zeros are these guys right here, and every once in a while they cross a phase zero. So what they're doing is making the Einstein-Lorentz transformed xt coordinate system. That's what I mean by getting special relativity just handed to you. The light waves just hands it to you. It's got it all mapped out, okay? So now we have to look at the dimensions of these little rhombuses here. And you'll notice in the, and I'll go ahead here, I should point out something real quick, though, is that it would be really expensive to do this. If you take a rocket ship with, you know, all of the equipment that you could live in, and take it to a speed of what we're seeing here, and that speed you can see rather clearly by the slope of this line right here. The slope of this line is telling you how fast the thing is going. That the group line right here, and that thing. And you can see that at the three distance here has been done in, let's see if I take this thing to its, go right up here on that line to this point, 5. So it's gone 3 in 5 units. That means it's gone 3/5 the speed of light. This is really fast. I mean, something comes through here 3/5 the speed of light, and in a second it's back 3 times around the world. It's more than 3 times around the world in a second. Now you all know, you know, what we're going to be claiming here is that the contraction, this is the Lorentz contraction due to the speed that Bob sees Alice and Carla, okay? It's going from here, about that big, to here, and then his time is dilated, slowed down, he's not ticking as fast, okay? That's the other things you see, but mainly what you see is the idea of future and past for Alice and Carla is very warped according to Bob. Over here he sees into their past, over here he gets to look in their future. That's the real magic of relativity, it cockeyes the time. Okay, so all three of those things are being displayed here. Now what I mentioned before was that when we had them like this, the group was flat with zero slope, and that means zero speed for the group zeros, and this was infinitely fast. And I passed up on that, and I passed that point of pointing out that the phase wave goes infinitely fast, in the sense that, I'll just back up here, because this really is a point that should be emphasized. These guys are infinitely fast. As you go through the thing here, every half period you get a bang, where the zeros are everywhere. And then a half period later, bang, it happens again. That's what it means to say that this is infinite speed here. We're talking about infinite speed for that kind of wave, whereas this one has zero slope and doesn't go anywhere on this diagram. Is that clear? Because that's a really important point there. Okay. Now, what we've got with this thing is more modern. What we've got with this thing is a phase wave that is faster than light. This is how fast light goes, but not infinitely fast. That was this. This is slowed down. Where the group used to be zero, it's now up to here. And I'm talking about this thing right here is the new space axis. So the phase vectors in this space are controlling space. The group vector in this thing is controlling the time. Those are the timeline. That's where you're going to put your new time axis. This is where you're going to put your new x-axis. Pretty neat. Waves are really helpful. But, come back to this. If I run somebody at 3/5 speed of light, I calculate it's about 10 gross national products of everything. That's how much energy at a dime a kilowatt hour. Okay? So, and so we got to do about 10 gross national products of the Earth, and then 20 to get Carla going. Well, let's cheapen that up a little bit. We could get Bob going for only one of those units. But how about doing it for a few cents and have some sense? Bob's stationary, they're all stationary. They simply tune up 1200 terahertz, which is the Doppler shift he's going to see for that one, and she tunes down to 300 and we play with that. So that's a doable experiment. And then it's just a matter of having Bob do some really fast counting. So that's what we're talking about here. Is we're talking about, once again, factoring these two, the R prime should have been red, just like that one, factor it into a group wave and a phase wave. But now they're more complicated because all these numbers are different. Now you're talking about a phase wave that's got a certain coordinates here, and the group wave that's got similar coordinates, but they're flipped around the 45-degree line. And that's called a Minkowski plot. We'll talk about Mr. Minkowski very shortly here. So let's do some analysis of this. Now remember, when you do a blue shift, and you're going to be taking a half sum of, when you're talking about the frequencies, okay, we're talking about the phase frequency and the phase wave number for the pitcher's mound, okay, the new pitcher's mound, the new phase vector, okay, the R prime plus L prime. It consists of one of these things, right, that's got a e to the plus rho, and plus one of these things that's e to the minus rho, okay? So we're talking about here a number 2, and then here a number of half. So we took about 5 halves, 5/4, okay? But that is going to be this number here. Now, if I think I may have left off a half in doing that. So this should be actually 5/4 and 3/4, and it is that later on. But the same thing happens down here, where I'm looking at the group, okay? It's the half difference, so I get a difference here and a sum here instead of the opposite up here. In any case, these sums and differences of exponents are giving us hyperbolic cosine, hyperbolic sine. That's just like the sine and cosine of the ordinary rotations that you get in xy space, but this is in space and time. So this is already giving us the algebra, and if I get your half back on there, we'll have the rest of it. This is a picture of Perspacetime, all marked off with the various values. In this case, a hyperbolic sine here, hyperbolic cosine here. And then this one has hyperbolic cosine here and hyperbolic sine there. Okay. This guy's flip over here, same thing, hyperbolic sine cos instead of the reverse, and this one is the cos first and sine second. Cos being that, this being sine. Okay, that's hyperbolic. Okay, so for this vector here, the cosine is in the right place that we're used to in sophomore physics, and the sine is on the vertical. This is the one that's got it flipped. And then the other trigonometric functions are there. Now, that's something we have to take a look at. But at this point, it's real easy to take the ratio of the frequency, say, of the group and the wave number of the group, the nu prime and the kappa prime, that's hyperbolic sine over hyperbolic cosine, and you get a hyperbolic tangent. So my little 1/2 doesn't hurt me here. That's the 3/5 that I was talking about, that this slope represents. And then this is 5/3, just the opposite. Okay, so at this point, I think we might just have a break. And by the way, this figure 11 in the text I just gave you is the way it should be. Here, I've got 2 full waves in each unit cell of the space-time. And here we don't talk that way, but there's the rhombus that mirrors that one. So it's very much like crystal physics, where you have a reciprocal space to do X-ray data in, right? And then you live in the space with your crystal as far as geometrical structure and the physics of solid-state physics. These are the parameters that completely define things. Old-fashioned notation. We'll stop and come back to that.